So I will be discussing quantum machine learning. And maybe I start with a disclaimer that probably quantum machine learning is kind of one of the most overhyped and underestimated fields right now. So we'll try to get rid of some of the hype and try to figure out ways of dealing with some of the bottlenecks. So really I try to understand what is really the power of quantum machine learning and what quantum computing can do for the machine learning applications. So here is the main question that I want to answer. It's not clear that I will answer it, but at least I want to pose the question, which is, when can we reasonably expect quantum computing to provide practical performance advantages over classical approaches in machine learning? Okay? So this is a very speculative and difficult question to answer. So what I will do is try to rephrase the question and say, how can we actually accelerate this process? Okay, so how can we make that it takes less time than we think it should take? Okay, so this is what I will try to do in this talk. And let me start also by saying that there are two different methodologies that one can use for quantum machine learning, the same way as for most quantum algorithms. The first one has to do with NISQ heuristics. Okay, so I will be talking mostly about quantum neural networks and this sort of parameterized circuits. Okay, and the second is quantum algorithms that, as we said, are a little bit more down the road. And these are algorithms that can provably do some things faster than classical algorithms. And some of the things that they can do faster have to do with classification, or with clustering, or with dimensionality reduction. These are kind of what people traditionally use in classical machine learning. And we will be discussing both of these topics. So I am not a consultant, but I learned how to do a 2x2 thing, so I'm very proud. So here is what we're trying to do, right? So on one axis, we have the hardware requirements of the algorithms. Okay, on the other axis, we have the impact that the application will actually have. And here is where we want to be, obviously. We want to have small hardware requirements, and we want to have high impact. So why wouldn't we want to do that? So here is where we kind of are. We have NISQ heuristics that you can actually run on hardware that we have now. Okay, their impact is not big right now. They cannot solve anything that we cannot solve classically. So the hope is that as the hardware evolves and as the heuristics become better, then their impact will also grow. Okay, and at the same time, we have the QML algorithms that I can prove to you that they have a great impact because they can solve things much faster, but they will need a lot of hardware that they don't have today. Okay, so what are we going to try to do? Where we're going to push both directions in order to get our holy grail. And because I'm a scientist, I can put a more realistic goal, which is somewhere in the middle, and we'll try to go there. Okay, so let's see how we can try to reach that slightly more realistic goal. So the first question I wanted to ask is, why quantum machine learning? Why do I think that quantum machine learning is really a good area where I believe that quantum computing can actually have an impact? So here are some of the reasons for being optimistic, cautiously optimistic, but still optimistic. So the first one is that we have some very powerful quantum tools that have to do with the computational core of machine learning, which is basically linear algebra. So people who are familiar with machine learning, you know that at the bottom of all these algorithms, whether they are deep learning and neural networks or other types of classification or clustering, support vector machines and all these types of algorithms, there is a part that has to do with linear algebra. You're multiplying matrices, you're trying to solve linear systems and things like that. So we do have some very powerful quantum algorithms to solve this type of problems. Okay? So this is one of the reasons why I think that quantum machine learning is really an area where quantum can actually offer something, because this is one of the areas where we do have quantum algorithms for this type of problems. The second thing that it's very interesting is that, as we said this morning, if you want to consider a quantum state, then you can see the state as some point in the sphere. For example, on Earth, as we said, it's not only on the poles, but it's somewhere. You can even think of a sphere not in 3 dimensions, but in many more dimensions. So the main idea is that if I give you these 2 quantum states, that these are some points in some space, the same as you have data points in your data sets. One thing that quantum computers can do very fast is figure out how similar, how far or how close these points are. Okay? And this is something fundamental for machine learning. For example, when we want to classify things or we want to cluster things, we want to check the similarity of our data points. Okay? So this is one other aspect of machine learning that the quantum computer can do pretty fast, which is figuring out the similarity or difference between different data points. Okay? So here is a third reason, and to me it's very important, and I think it was also hinted in the morning. Machine learning is not an exact science. So and this is good news for us, because when we want to say that we have a quantum machine or a classical machine learning algorithm that works, this means that we have algorithms that are extremely resilient to noise. If you want your autonomous vehicle to be able to recognize the signals and the signs in the street, it has to do it in a way which is extremely resilient in noise. It could be raining, it could be lighting, it could not be light, it could be day, it could be night. So we have already a lot of noise in our data, but nevertheless, the machine learning algorithms can actually deal with this noise. Okay? So why is this interesting for a quantum computing point of view? Because quantum computers will also add noise to our computation. They're not going to be exact. We are going to have noisy machines, okay? But we are using noisy machines for an area and for a type of problem where already there is noise in the data, and we have to find ways to deal with noise anyways. So the goal and the hope is that given that we have to deal with noise and we have ways of dealing with all this noise that exists in the data of machine learning, the hope is that the extra noise that will be coming from the processes, from the quantum machine, would also be something that could potentially be handled. Okay? For example, if we are really training neural networks right now, classically, then we actually inject noise artificially into the computation in order to make our algorithms resilient. So with the quantum machine, we don't have to inject noise because our hardware is already noisy enough that they do our job for us. And here is another thing that I want to be very clear about, is that there are many different things that one could try to improve when it comes to machine learning, right? So it's only one thing to say I want to be faster. So yes, we can try to come up with algorithms that are faster, okay? But we can also try to come with algorithms that are more accurate. They might take the same time than the classical algorithm, but they give you better results, okay? Or there are 2 other options, 2 other things that are very important, and they're becoming increasingly important. The first one is this notion of interpretability. What does this mean? It means that for many sectors, for many industry sectors, for example, when I talk to the healthcare people or to defense, so what they say is that it's great that deep learning works, but I cannot really use it. And I cannot use it because I cannot explain how it works. And this really makes it impossible to actually deploy this type of algorithms. So we have to go back to using more interpretable kind of models and more interpretable kind of algorithms. And this is what quantum can also offer something, because we can make the interpretable algorithms, like, for example, support vector machines or feature selections, in a way faster and more accurate. And the last one is about energy saving. So we know that classical machine learning also works very well for specific tasks, but we also know that it's extremely energy consuming. So one other area where we can try to improve is by saying that a quantum computer may not give you a faster solution or a better solution, but it can really decrease your energy consumption. And this is quite important. The more data that we're going to be having, and the more we will be using these techniques everywhere in the industry. So these were the reasons to be optimistic. So there are also many reasons to be very cautious about it, and I will just also want to mention a few of them. The first one is basically the same as the one of the reasons to be optimistic, which is that we have some very powerful quantum tools for this, what we call this linear algebra, but they are extremely subtle, meaning that it's not a black box thing that you can just press the button and say, I know that it will always work better than my classical algorithm. These are extremely subtle techniques that you really need to understand what is the problem you're talking about, what is your data that you're running your problem on, and what specific variants of these algorithms do you really need to deploy in order to actually try and get the speed up at the end. Okay? So these are extremely subtle tools, and they're not going to work always. Okay? The second is that if we want to discuss a bit, if we want to get the full power of quantum computing when it comes to quantum machine learning, one of the things that we have used quite a bit is the ability to take all this classical data that we have and somehow load this classical data in a quantum way so that the quantum computer can actually do these computations much faster. Okay? So there is this issue of how do we take the classical data and map it into some quantum states that can be manipulated by these quantum algorithms and the quantum hardware. So this is not a simple problem, okay? But I will show you a little bit further down the talk how we can try to actually do something interesting about this. The third point that I wanted to make is that when we try to solve these machine learning problems with a quantum computer, what we get most of the times out of this quantum algorithm is not a classical answer, but it's a quantum output that somehow encodes this classical answer that we want into this quantum system. So somehow we need to go into this quantum system, and by performing some observations, some measurements, we need to extract the classical information that we really care about from these quantum states, from these outputs of the quantum algorithms. Again, depending on what type of information we may need to extract, it might be very simple, or it might also take a lot of time. So this is also something that we need to take care about. Not, on one hand, how do we take our inputs and put them into the quantum algorithm? On the other hand, how this quantum output can actually come out as a classical answer that we can use in the remaining workflow. And here is the last one. So as I said, machine learning works because it works in practice. It was also said in the morning that maybe what we care about is not proving that theoretically it should work, but actually see if it works in practice. And the reason that people believe that it works in practice is because they use it with real data and they get real outcomes and they figure out whether it actually works well or not. Okay? So here, many of these quantum machine learning algorithms and most of all these quantum heuristics, they're proposals of ways of trying to do things, but there is a big caveat, which is that we don't have big enough hardware to actually test whether they actually work well in practice or not. So it is not very easy to benchmark a quantum heuristic if not, on one hand, you don't have a mathematical proof that it works, but that's okay. It would have been okay if you could actually see whether it works in practice or not. But for that, we need also hardware. So we are in a case where there are many ideas out there, but it's difficult to figure out which one of them are going to work or not. Okay? We have some idea by trying to implement very, very tiny examples of this, but the more the hardware will getting better, the more we realize and will understand what type of heuristics work better and what types of heuristics do not work so well. Okay? So we are waiting for hardware in order to be able to benchmark a lot of these algorithms. Okay, so how do we enhance classical machine learning? So I will discuss briefly the NISQ heuristics, and then I will go more into the algorithms. I wanted to tell you that on the third day, on Thursday in the morning, we have a very nice session with scientific talks that are focused on the NISQ heuristics for quantum machine learning as well. So there are many different proposals for what the quantum neural network should look like. Okay, I cited a few papers, but there are even more papers than this. Here is what they look like. I don't expect you to understand many of these. I don't understand half of them either. But somehow what I wanted to tell you is that given the fact that it's not very clear how to test what things work or not, there are many different proposals that we are in the process of trying to understand how well they can actually perform. So let me try to just describe in high level what these quantum neural networks look like. Okay? So the idea is that you have some quantum circuit. Okay? What is the circuit? The circuit is something that takes an input that could be an image of a cat. Okay? It takes this input through this procedure, through this quantum circuit, and at the end the circuit should tell you this is a cat or this is a dog. right? So I'm caricaturing a bit, but let's say this is one of the things that one would want to do in machine learning. So how are you trying to find this circuit that would actually do this thing? Like when you give it a cat, it should say a cat, and when you give it a dog, it should give it a dog, right? So what you do is that you parameterize the circuit with a number of parameters or variables, these phi's and thetas over there. In the beginning, you randomly assign values to this, and you try to figure out if your circuit works or not. So obviously, it's not going to work in the beginning. So what you do is that you try to understand how you can improve these parameters in order, little by little, to come up with a circuit that you believe that it will recognize the cats from the dogs. Okay, so this is what the training of this quantum neural network will be, is figuring out exactly what are these parameters in these gates that you apply into this quantum circuit. So this is not very different in some sense with classical neural networks, where still you have some sort of circuit that you input an image, you need to get at the end a label, and what you do when we say about training neural networks is exactly figuring out what parameters we need to put into these edges of the neural network in order for the classification to happen with high probability. Okay? So, as I said, it's a very interesting research area, but there is a lot more work that is needed to be done, right? So the hope here is that given that these quantum states live in a much, much higher space, what we call this exponential Hilbert space, the hope is that when you train these quantum neural networks instead of classical neural networks, you can take advantage of the fact that you are in a much bigger space, meaning that you can come up with models that were not even possible to come up with in a classical world, and figure out ways of doing this type of tasks by using richer models and hopefully achieving higher accuracy when you are doing this type of tasks. Okay? So they seem to work okay for extremely small instances. So this is good news in the sense that if you couldn't even make them work for very tiny inputs, then the hope that they will actually work when you scale them up, then it would not be great. So they do work okay for small instances and simple kind of data sets. So the hope is that they will continue to work for better, for bigger instances and larger hardware. As I said, it's very difficult to benchmark because we're missing the hardware, okay, when it comes to these heuristics. One other thing that it's important for me to say is that these are heuristics that are good, that we hope they are good for some specific problems, but these are not something that will solve all your possible problems. Like, it's like I give you a screwdriver and you try to put a nail on the wall. That's not what it's supposed to do. So these are heuristics that one can hope that they work well for problems like classification, okay? They are pretty surely not working well for other problems where even classical neural networks do not work well, for example, right? Okay, so what I try to say is that we have all these different types of ways of defining quantum neural networks. They're very interesting, and the main hope is as the hardware also becomes better, that their impact will grow, because on one hand, we will be able to understand which ones of these heuristics actually work. We will be able to test them in larger instances using the bigger hardware, and hopefully we can move these techniques towards something that it makes sense. So let me go now to the quantum machine learning algorithms. So here is one of the first applications that we came up with a couple of years ago. So it kind of made the news for many different reasons. So here is how we define this problem. The problem is a very simple problem. You have a number of users, you have some products, and what you want to do is you have this matrix where you see if a user likes a product or not. And then what you would like is to find a product for which you don't have information if the user will like this product or not, and recommend a product that with high probability the user will have a lot of utility for, right? So for example, this is what you do, what Netflix does. If you watch this movie and that movie, then you should possibly like the third movie, and this is what the recommendation will do, okay? So I'm using here a very schematic way of talking about it. So I'm assuming that we have 100 million users, 100 million products. But as you know, even though we think that we are all very unique, we are not very unique. There are not so many different types of users. So if you want, 99.5% of all users fall into some 100 categories. And if you have something like that, which is basically the parameters that you have for something like the Amazon preference matrix, then the classical algorithm will need 1 trillion steps to run, okay? And this is what we did a few years ago. So we found out a quantum algorithm that will use 1,000 steps to run, okay? So obviously a quantum step might be slower than a classical step. So this is not exactly what you expect to see in practice. But theoretically, this is the number of steps that the quantum algorithm will need, which is 1,000 versus 1 trillion. So this is quite big of a gap. And the hope is that part of this big gap, you can actually see it in practice once we have these quantum machines running. Okay. What happened after we proposed this result? This result had what we call an exponential gap between the classical and the quantum case. Okay. So then there was a question, is the exponential gap the best, is there really an exponential gap between the classical and the quantum case, or can classical algorithms actually do better as well, right? So then there was a new result, which was called like a quantum-inspired result by Yuan Tang in last year, which is an extremely interesting theoretical result that actually says that the gap that we thought was exponential is not actually exponential, but it's only polynomial. So you saw a little bit from last talk that exponential is good, polynomial is bad, or let's say polynomial is worse. But when you actually apply these results for the specific type of matrices, the 100 million and stuff, what you get for the quantum-inspired algorithm is that you need 1 billion of trillion steps. So even though we got from an exponential gap to a polynomial gap, the actual gap between the quantum algorithm and the classical one is even more than what it used to be with the old classical ones. Okay, so why am I saying all this? I'm just saying that quantum algorithms and classical algorithms are extremely important to get into the details and figure out really what does it mean for my application. It's one level of understanding, is there a polynomial gap or is there an exponential gap? This is very interesting and very important to understand. But please continue to talk to the scientists and continue to get information about your specific use cases. This is the only way we can hope to have real quantum applications, is if we start talking about the specific use cases and how all these gaps translate in reality. Okay? So there are more examples. Image recognition, this is something that we did last year. We started from the most basic and simplest data that exists out there in the machine learning world, is this 100 digits. We use the MNIST data set. One can see, if you just multiply all these things, that the classical thing can take 10 trillion steps, and the quantum can take 10 million steps. This is a smaller gap than we had for the recommendation system, but there's still a decent gap between the two, which means that if we put all the overhead that the quantum thing needs, maybe in practice we will actually see some difference. The same thing with clustering. I just want to go into this. So we talked in the beginning of the talk about quantum neural networks. This is trying to come up with quantum analogs of the classical neural networks. There is another thing that we try to do, which is go back to the classical neural networks. And why is that? Because we know that they work. And the question is, can we speed up the training of these classical neural networks? Okay? So here we are not trying to define new quantum ways of doing neural networks, but we look at the classical ones and we say, can we speed up the training? Because this is the real bottleneck in deep learning. How do you train these classical neural networks? And we do have some results that show that you can get some speed ups when it comes to the classical versus the quantum training of the neural networks. Okay, so for now, all the algorithms that I showed you are somewhere there at the very top right corner, meaning that for now I did not tell you anything about how easy it is to actually implement these things, or how fast or in how many years or what type of hardware requirements you have. And the first answer is that if you just read the papers and you stop there, then they do need many qubits, and they do need many years before we'll have the computers to actually run them, okay? But here's what I want to do, and I want to finish the last few talks about this. How do we bring this closer to the hardware requirements that we have today or that we will have in the mid-scale? And I want to make this very clear that if we try to accelerate the moment when we will really come up with real-world applications of quantum computing, if we just say the algorithm needs 10 million qubits, so let me just wait until the hardware reaches 11 million qubits, then this is not going to go very far. So what we need to do is work on both sides. The hardware should be getting better, but should be getting better in a user-driven way. We need to tell the hardware what we want to solve, okay? And we need to take all these algorithms that we expect them today or yesterday to use 1 million or 10 million qubits and figure out how do we bring them closer to what the hardware can do. Maybe not now, but in 3 years, not in 25 years. So here are some of the things of what we are trying to do. So you know what NISQ is. I think it's so popular now that we can even use it as a verb. So we are now NISQifying the QML algorithms. So one aspect is, as I said, how do we load classical data into the quantum machines? This is one of the assumptions that we made in order to get all these amazing speed-ups that we had. How do we do that? Well, there are many proposals out there. They are not very practical. These are also QRAMs that I found on the internet, so you can either think of them like that. But one way of dealing with this thing is to start saying that, no, this is very unrealistic, this is impossible, the hardware will never be done, so quantum machine learning is never going to work. So this is exactly what also people were saying 10 years ago or 20 years ago about quantum computing, that could be unrealistic and impossible, but we are here today. So the way that we want to think about it is that if the hardware is too difficult to build, let's go back to the drawing board and let's fix the algorithms. It's not only the hardware that needs to get better, it's also the algorithms that need to get better. So we went back and we said, do we really need everything that this QRAM is supposed to be doing that makes it very difficult to implement, or can we get away with something which is simpler to implement? And this is what we came up with, these quantum data loaders. They're as powerful as these random access memory things are, in the sense that we can use them to do what we needed for the algorithms, for solving the use cases, and they're much simpler to implement, and also they're much more robust to noise. The same thing with linear algebra. Linear algebra also is something that, if you just look at the papers, it's something that is not very easy to implement. You do need large quantum computers, and most probably fault tolerant. The question is, okay, do we need the full-blown quantum linear algebra if we want to really solve machine learning problems, or can we get away with simpler things? So we try to look much more in detail in this. And yes, if you want to train neural networks, for example, or if you want to do classification, you don't need to use the most elaborate quantum algorithms that do linear algebra. You need specific quantum algorithms that solve matrix multiplication fast and very specific operations. And for that, there are much better circuits with fewer qubits and much more shallow circuits than one would think in the beginning. The same thing with everything, with distance estimation, with extracting the classical information. The main point I want to make is that if we need to bridge the gap between what we can do today and what we hope to do tomorrow, then we need to work on both sides. We need to improve the hardware, but we need to improve it in an intelligent way that makes sense for the applications that we need to use the hardware for. And we need to go back and we need really algorithmic expertise to look at the algorithms and bring them closer to the NISQ era. So let me finish with this. When can we reasonably expect quantum computing to provide practical performance advantages over classical approaches in machine learning? This was a mouthful, but I'm not going to give you a number. But what I'm optimistic enough to say that it should be sooner than we initially thought, and we need to work both on the hardware and on the software to make this actually work. So thank you very much. So there is time for one question before lunch.
On your very last point, can you give us the date that
the month or the day?
Well, I want the date. Well, at least give us the date that you quote initially thought.
Oh, I see. So I'm one of these very going old people that started doing quantum algorithms in 1999. So I have 20 years working on this. And when I started doing quantum algorithms in 1999, if someone would have asked me, when are quantum computers going to happen, I would just laugh and say, I don't care, I'm just doing math. So at that point, it was infinite, the time, right? Now, if you go back and you see this, for example, this HHL algorithm, and you look at, if you just naively try to implement it, how many qubits do you need? Then you are getting on some millions of qubits. Okay? So what we're trying to do is figure out how to solve specific use cases with algorithms that will need much fewer qubits than that, okay? And get as much power as we can from whatever hardware is available, but also drive what architectures the hardware should also be trying to do. I really believe that the hardware and the software people should be getting together, and it's not, the difference of solving a problem is not 100 qubits or 200 qubits, is what can these qubits actually do. And if you know what you're trying to do before you're building this machine, you can build it much better.